In 2016, Maverick Applied Science developed the Plant Engineers FRP Forum to create a platform where plant engineers could come together for in-depth discussions and exchange ideas on matters related to FRP equipment and piping reliability. After the success of the forum in 2016, we presented the second annual Plant Engineers FRP Forum on May 10th and 11th, 2017. The 2017 forum included 20 presentations and discussions on FRP and dual laminate equipment with attendees from all over the country. Discussions range from FRP scrubber designs, the merits of the RTP1 standard, shop inspection expectations, acoustic emission testing, and fluoropolymers. The depth of the content was truly impressive. Since everyone was not able to attend, we would like to share some of these presentations by webcast to the general industrial community.
Hopefully you all have had your coffee and your sugar, because we're going to lay some heavy FRP on you this morning. We've got Daryl McCulloch going to talk about tank nozzle load evaluations.
Yay. Thank you. Thank you. Yes, if you remember me from yesterday, so basically, whenever I'm up at the podium, expect a little more technical, heavy content. So I apologize if you don't like that. It's first one of the day on Friday. Yes, I hope you have had a chance to get some coffee. But there are generic understandings I'd like to get across beyond the technical content. If you like the technical content, I handed out my cards. I'm happy to talk about anything kind of specifically after, but there's kind of a main issue that I just want to kind of get across to you today. So general outline, won't spend too much time here. We'll go introduction, kind of background of the issue. Then we'll get into determining tank nozzle stiffness, specifically for FRP vessels. And then we'll go through the evaluation of nozzle load. So there's kind of a progression of events throughout this presentation and throughout the process for how to make sure your tank reinforcement pad or gussets or whatever is designed appropriately. So some of the background. Currently in RTP1, it has in the design section for sustained loads, it says the tank design must consider loads imposed by piping. Okay, well, you know, that's good in theory. I can promise you it's poorly done in practice. Chiefly being because it is very rare that the tank manufacturer and the pipe manufacturer are the same person. It does happen, but I mentioned yesterday, basically tank designer wants to go up to the end of their nozzle flange and say, you know, nothing is, you know, imposed on my tank. Piping designer goes up to the tank and says, I don't care about the tank. This is where my anchor point is. So there's a discontinuity there, just in how this is evaluated, because truthfully nothing is rigid. We'll talk a little bit about that as we go on. You know, the common misconception is that, well, let's just put an expansion joint in there, right? That'll solve all the problem between, you know, the piping and the tank. And, I mean, maybe, but not necessarily. So, like I said, RTP1 says you have to consider loads, external loads imposed on your tank. Then there's also some fine print in RTP1 that says, you know, it's recommended for all connections to be, you know, isolated through flexible connections. So that's kind of their catch-all of saying, well, okay, we do have to consider external nozzle loads, but you should really use expansion joints so it kind of, you know, alleviates the responsibility from us. So to kind of illustrate this kind of issue with an example, I think this could be somewhat enlightening to help you understand kind of the crux of the problem. So general pipe stress example. So we're going to say this is your tank connection here, and this is just a typical rigid anchor support. And we're okay with calling this one rigid in this case. Just a support here. It's got a dead weight support with guide, so basically it's allowed to go that way. It can't go that way more than 1/8 of an inch. So we're going to apply temperature and obviously dead weight to this. So this is going to want to grow this way. This is going to want to grow this way. And what's happening at those connections. So we're going to examine it with a couple different assumptions. So, first assumption, if we assume this is completely rigid, which is something in the order of 10 to the 10 magnitude of pound per inch or inch pound per inch if it was a moment, the rotational direction. So when we analyze just this section with this rigid, it's pretty bound up. So with a high stiffness, we have a moment of over 3,000 foot-pounds. If you give that to a tank manufacturer, they're going to laugh at you and say, that's impossible. The pipe stress alone is almost 5,000 psi, which is overstressed in the pipe. Just like I said, it's extremely bound up. So if somebody is looking at this in isolation, the pipe analyst doesn't care what the tank looks like. It could be 20-foot diameter, it could be 2-foot diameter, they don't really care. The solution to this problem would probably be put an expansion joint in. Okay, well that's all well and good. Expansion joints are sometimes seen as a kind of a catch-all problem. Rob mentioned it yesterday about if you have some misalignments, throw an expansion joint in there. So expansion joints, they may seem somewhat simple. I hope Rob, he tried to explain it a little bit yesterday too. They definitely require different consideration because basically you're breaking your pipe in half, so now you need extra supports in here. You have pressure thrust issues, not to mention the reliability issues of just leak points. They're maintenance items. So if you put an expansion joint in here, well, you have the cost of the expansion joint, you have some more flanges you have to buy, you have some more hardware you have to buy, you have an extra support you have to buy. So a lot of ramifications just by the simple assumption of saying you have a completely rigid connection. So let's say if we assume a reasonable stiffness, and I'm going to say something in the order of 10 to the 4 magnitudes, and quite a bit lower, all of a sudden we're about 10% of the moment, and a little bit more than 10% of the pipe stress, which is all of a sudden acceptable. So basically now we know this is kind of free to rotate somewhat. There is some finite flexibility. Nothing in this world is completely rigid. Even some of the later examples when we're examining steel tank stiffness, even steel tank nozzles are somewhere in the order of 10 to the 7. So 10 to the 10 is just beyond unreasonable for an anchor connection at a tank at least. If you're at a pump, say a pump is rigid, that's really not going to be moving. So this kind of highlights the importance of assuming some sort of a stiffness, a finite stiffness for tank connections. Now, just because the pipe stress is acceptable, that doesn't mean the tank is okay because 394 foot-pounds is still up there. We'll talk more about magnitudes and where we're trying to get for acceptable loads or the process for determining acceptable loads a little bit later. So, I mean, is it fair to assume that these tank nozzles are completely rigid? There's a number of different factors that go into this. You have tank diameter plays a big factor in it, nozzle diameter, reinforcement, thickness of tank, and probably the biggest thing that I'm going to highlight today is the material of construction being FRP. It's not isotropic, you have different material properties in different directions, which has significant influence. Okay, so that's all well and good. So how do you estimate the nozzle stiffness? How do you get to that 10 to the 4 magnitude of stiffness? Currently there's a couple different ways. Well, primarily you're going to look at WRC 297. So that's Welding Research Council document 297. This is very old, as you'll see on one of the next slides. There's a curve that's just kind of handwritten and it's extremely old and it's not even a digital copy really. But they determine curves, generic curves through their testing to determine the stiffness factors. There's limited applicability because they only did a certain amount of curves and then you have to interpolate or extrapolate, which is extremely dangerous in its own right. They're tough to read, and the biggest thing is they're developed for steel. So that's, like I said, an isotropic material. We are not an isotropic material. Even type 1 and type 2 laminates, they're kind of quasi-isotropic. I'm not going to get into that, but they're not exactly homogeneous isotropic materials. The other method of analysis that's a little more accurate is to do FEA on it. So time consuming, I have in parentheses there. Basically time consuming means, yeah, it's probably going to cost you a little bit more than might think it should cost to determine tank nozzle stiffness. So here's the curve I was talking about. There's two curves, one for radial stiffness and one for rotational stiffness. You don't need to see anything on here, just that it's old, there's several curves, could be hard to read, and a lot of room for interpolation, and there's actually very limited applicability because of how few curves there actually are on there. So basically the way to do WRC 297 procedure, figure out your geometry parameters, and that's based on everything down here below. Read the factors from the curves, calculate the stiffness. Pretty simple. You know, maybe. The things you need to determine these geometry parameters, tank nozzle diameter, tank nozzle thickness, material modulus, shell height, where the nozzle is located in the shell. Well, how many pipe designers do you know that are given this information? I don't know too many. So unless you're doing the tank design and the piping design, it's a black hole. You're not going to get this information unless you specifically ask for it. So here would be an FEA example of something we've done, or we would do, to determine nozzle stiffness instead of using WRC, especially when you're dealing with an FRP material. To be honest, an experienced analyst, I mean, we can figure out stiffness in just about as much time as to go through the whole WRC process. It's not that onerous. I mean, this is not a complicated model to figure this out. And the upside of that is the model can also be used for the stress evaluation that we'll talk about later in the presentation. So what we did, we wanted to see how good the WRC approach actually was. So we did a comparison of FEA and WRC, and this was just assuming steel material. We wanted to see how close the curves actually were. We stayed within the parameters of reading the curves, so we knew there's no misinterpretation of the curves to see how the numbers shook out. And you can see it's fairly reasonable, you know, -3, -10%. You know, basically that means the WRC assumptions are underestimating the stiffness. Underestimation of stiffness means more flexible, means lower nozzle load, so that could actually be unconservative. Now in the longitudinal direction, you have a little bit more variance of up to 24%. Now I'm here to kind of tell you that the magnitude, the order of magnitudes is more important than the exact number. So 10 to the 4, somewhere in that range of a 10 to the 4 exponent is more important than knowing it's 50,000 pounds per inch or 40,000 pounds per inch. So these percentage differences, to me, they get you close enough. Now again, the WRC assumptions, homogeneous material, there's no local reinforcement or gussets on those curves. Parameters are readable on the curves, so that's the assumption that whatever your tank, you know, nozzle diameter is fits on those curves, or else you're kind of, you know, up a creek. And like I said, it may underestimate the radial and circumferential stiffness. So what would we recommend if you're using WRC? Well, like I said, more flexible means lower load. So we would recommend to do calculations to get you the maximum stiffness. So that's things using maximum thickness of the tank, the nozzle, max properties, use the nozzle OD instead of the nozzle ID, so you can over-predict the stiffness. So I've been talking a little bit about film and mount, so let me introduce this. So Tom talked, we talked several presentations yesterday about film and wound tanks, where you have axial direction glass and you have hoop direction glass, and you bias that hoop direction glass to whatever optimizes your design. So you're going to have, in a tank, you're going to have more hoop stiffness than axial stiffness. Well, that just throws a wrench in the whole isotropic assumption. So the stiffer something is, the more load it carries. So the hoop direction is going to carry more load, so it kind of distorts the curves a little bit. So if you were doing an FRP nozzle, trying to calculate the stiffness, we would recommend, so you divide by the elastic modulus, basically whatever you're using to read the curves, the isotropic elastic modulus, and then you just multiply by the effective modulus between the hoop and the axial direction, and that kind of gets you pretty close. We'd also recommend use the OD of any gussets. So on small diameter nozzles, 4-inch and less, they're going to be gusseted. So say a 4-inch nozzle that has a 10-inch diameter repad, the gussets are going to go all the way up to the repad. So in effect, that's a 10-inch nozzle that you're evaluating. So like I said, this should get you close, and then the piping designer calculates the loads. So your tank manufacturer should be supplying the stiffnesses on nozzles of importance. So say at a pump connection, you would say, okay, what's the stiffness of those nozzles providing the stiffness? Some people want to say give me the allowable nozzle loads. That's kind of a mixed bag. Talk more about in detail why there's some variance in that a little bit later, but it's going to be very conservative if you just tell your tank manufacturer to give me allowable nozzle loads. It's a more optimized design to say, give me the stiffness, pipe designer will do the analysis, give you the loads back into the tank designer's hands to design the repad. Okay, so enough with stiffness. Let's talk about how we actually evaluate those nozzle loads. So you got the stiffness, you did the pipe stress, you got your loads on your tank connection. So what do we do for nozzle load evaluation? Okay, the important loads to consider are the radial load, straight in, and your bending moments in longitudinal and circumferential. There are 3 other directions. There's lateral this way, vertical force that way, just shear forces, and then torsion on the nozzle. Now those are fairly stiff, so we kind of ignore those, and you would probably just say those are rigid in the analysis, but those are not going to cause a great deal of stress. Important to note that all of those loads generate both hoop and axial stress, so it's not like you're just bending this here and it's only causing stress in the hoop direction. Bending this nozzle here, rotating it there, is going to cause hoop stress, and it's also going to cause axial stress. They all have influences on one another. So current ways to evaluate loads in industry, and not just FRP, WRC 107, 297, 537, talk a little bit about those. Bednar's pressure vessel design handbook, ISO or EN 13121, they all kind of share the same approach. That's all kind of based on the WRC approach, or you can do FEA. This is where having that model I was talking about earlier comes into play. So you have that model ready, you can apply the loads and see what repad you need to do. All of those approaches are based on homogeneous. Beat this with a dead horse, just so you understand. They're all based on isotropic. Everything in FRP world comes from steel. Our flange design comes from steel, and we just adapt it. Well, we have to make some changes, modifications, to make sure we're appropriately considering the unique nature of FRP construction. And the biggest thing is film and wound construction affects the stress distribution and the magnitude. We'll go in a little bit here on the upcoming slides. So a former colleague of mine, he was tasked with doing a research project on this, and he spent countless hours looking into this. And what he ended up doing is built, I don't know how many FEA models, somewhere over 300, I think. Vessels diameter 6 foot to 16 foot. We wanted to get a reasonable range of vessel diameters. Nozzle diameters between 6 inch and 48 inch. We chose 6 inch as the lowest and not 2, because what I was telling you with the gussets, a 2 inch basically turns into an 8 inch. So we want to do our evaluation irrespective of gussets and just say it's a 6 inch nozzle. Various thicknesses to see their influences. And one of the bigger assumptions is we place the nozzle at the mid-height. If you put your nozzle closer to your flat bottom knuckle, well, that's going to be more stiff. If it's near a rib, it's more stiff. We just needed to isolate those concerns and just say it's in the middle of the shell. We don't want to look at any other influences that might distort our results. We looked at isotropic material properties and quasi-isotropic, so type 1 or type 2, where you have the same modulus in the hoop and axial direction. Orthotropic, getting into fill and wound, where you have a bias of a 2-to-1 hoop to axial ratio, and then a higher bias of a 3-to-1 hoop to axial ratio. Now these are very involved curves. I'm not going to go into too much depth explaining them. We can talk about these if you want. All I'm looking at here is comparison of hoop stress due to the longitudinal moment. What I want to show here is these blue dots down here. Those are the isotropic assumption. And this is a normalized curve, so basically it's your FEA results divided by the WRC results. So if you're at 100%, well, that means the FEA and the WRC agree. So your isotropic assumptions, pretty good. Okay, and then you go to your 2-to-1 hoop to axial ratio. We're getting a little bit higher, where here you have some over 150%. That means the actual stress is 50% higher than the WRC would tell you it actually is. Okay, now you get into the 3-to-1 heavily biased, which I would say is not that abnormal, so this isn't out of the realm of possibility. you're over 200, it's called 225% stress. So that is significant. So we need to figure out a way to bring that down. So same curve, comparison to hoop stress due to longitudinal moment, but we modify it by another factor, which has to do with the hoop to axial modulus ratio. So we do that, we multiply that, or actually it's dividing by that ratio to normalize it, and now everything's around 100%. So that tells you there's something to that hoop to axial modulus ratio. Like I said earlier, a bending moment causes both hoop and axial stress. So the last one, we had hoop stress due to longitudinal moment, so circumferential moment is causing hoop stress as well. So these are reasonably predicted about 20% over, so not too bad, fairly close. Still not as influential as the longitudinal moment. And then hoop stress due to radial load, again, pretty good, and then it actually starts tapering off. So basically when you go that way on the curve, that's basically for larger nozzle diameters, so you have a larger circumference, more distribution of the load. Just putting all these graphs together, the reason why is because they're all hoop stress. They're not independent of each other. So all of these kind of add together to know your actual total magnitude of stress. And the last thing, the other assumption is about the stress distribution around the nozzle. So the max hoop stress due to the longitudinal moment is affected mostly by the film wall construction. So hopefully you saw that in the curves where you had the heavily biased 3-to-1 hoop to axial ratio cause the most stress. Well, hoop stresses, which is what we were just talking about, that's usually what the tank design is optimized for. Axial stress, these tanks are usually just sitting there unless you have an internal pressure case which could cause axial stress or overturning. But for the most part, your hoop stress is your governing, where you're sizing the shelf thickness for that hoop stress, which means you don't have any more available strength. So any nozzle load on here is just increasing the hoop stress, for which you don't really have any available strength left. Now, however, magnitude is not the only consideration. So with an isotropic assumption, here's a simple contour so you can kind of see. So isotropic assumption, let's just call it steel or type 1 or type 2. So the max stress due to MC is in the hoop direction. So this would be an MC circumferential moment. Max stress due to NL, longitudinal moment, is up here, and they're kind of isolated from one another. The max stress due to radial load can actually be either, and it depends on the configuration. Now the WRC approach combines the stress due to circumferential moment plus the radial load, and then it combines the stress due to the longitudinal moment plus the radial load, but they're not all combined. Well, this is kind of okay for an isotropic material, but what happens when we look at our 3-to-1 ratio? Well, this contour is getting a lot more closer to that zero direction. So that's telling you that circumferential moment is affecting that stress there, where we already know from the last slide that the longitudinal moment created the max stress there. So that means you have a lot of stress there from the longitudinal moment, plus whatever influence you have from here that's creeping over that you don't really see here. So again, another curve I'm not going to dwell too much on. Basically this is saying, this is our isotropic assumption, 0 to 90, and it kind of tracks the stress around the nozzle there, around the circumference. Well, what happens when we have either a 2-to-1 or 3-to-1 ratio is our stress is way higher than the isotropic assumptions there. So there's an influence around the nozzle there that we need to capture, that the WRC approaches don't, because they're just saying the stress due to circumferential moment plus radial, not all three together. So I'm not going to teach you how to do this. It's still kind of in development. There's no good standards out there, but I hope I have conveyed to you that there are resources out there that this can be done. So you don't have to say, well, I'm just going to believe the fabricator and we're just going to do expansion joints everywhere. But it's important to understand the limitations of WRC. Talked a little bit about that. It's, again, isotropic material assumptions. There's a lot of curves. If you're outside of that curve, I wouldn't trust it. And obviously there's additional considerations necessary for FRP. I'm not going to read those bottom ones, we've kind of talked about those enough, other than saying we would recommend to add all 3 stress component loadings of your circumferential moment, longitudinal moment, and radial force instead of just isolating 2 of the 3. So last slide, it was funny yesterday, I was talking about scrubbers not being able, you can't design a scrubber thing, it was just an atmospheric tank. So now I'm talking about tank nozzles. It could be a scrubber, it could be just an atmospheric storage tank. You can't design the tank nozzle without considering the piping loads. It's an iterative process, okay, yeah. We talked about yesterday the RTP1 stamp, so it's going to be a little bit of a headache for tank designers, manufacturers to get on board with RTP1. There's going to be some learning curve associated with that. There will be learning curve associated with this too. If tank designers now have to provide their nozzle stiffness values with their submittal, so then that can go to the pipe stress guy, so he can put it in his pipe stress analysis, so the pipe stress guy can get the reactions to get back to the tank designer, so they can size the repad appropriately. And because, I've said it before, I'll say it again, the tank design is going to be optimized. They're trying to save as much money as possible, so they're only designing the shell thickness as thick as it needs to be. The reinforcement pad that you see, the style A or style B that Jeff talked about yesterday, those are, again, they're just to restore the cutout you took for the nozzle. So the repad on the tanks, that's again just optimized for pressure. No consideration for extra nozzle loadings. So there is never 0 nozzle loads. Even expansion joints have some pressure thrust that goes back to the nozzle. So 0 is an impossible number. So there's always some loads. It's just a matter of what the magnitude is. You can provide we see on some drawings where they have maximum allowable nozzle loads. Well, that's kind of, what good is that? If the piping designer assumes the tank connection is perfectly rigid, we saw in that first example of the pipe stress, it's going to be impossible for them to get loads that are lower than 250 foot-pounds or 250, pounds for the radial force. Because in that pipe stress example, even our optimized design, that was something 400 foot-pounds. You don't see those as acceptable in a tank designer, so they're going to have to add some more repad to that. So there's no quick and easy way, but there are too many issues with nozzles and flanges in the industry, and we need to kind of come together and advance this and progress this, because this is what the steel industry does, and we can't just say, well, steel does it this way, so we're just going to copy them. We have to account for the differences in fiberglass. So I hope you at least took the basics out of that. I mean, if you want to talk about anything more in depth, I'd be happy to. But hopefully the general problem was shown. So I'm happy to take any questions.
Do you see more failures? Is this why you see more failures because they underestimate?
You see a lot of cracked flanges, and there's different reasons for that. Sometimes you see hanging heavy equipment off flanges, and if it doesn't have nozzle gussets, or even if it does have nozzle gussets, you'll crack a flange. Sometimes flanges are cracked because they don't part apart right, or they're bolting a flat face up to a raised face and they're just wrenching down on the flange. But yes, you do. It's not as often you see tank issues. You see, path of least resistance. So if your flange is the most flexible part, you might crack the flange. But yes, it is absolutely an issue in the industry.
Daryl, you're approaching this with nozzle attaching to the tank and repad. The flange itself, you're kind of limited as to how much reinforcement you can actually put on the flange.
Yeah.
Neck and part of the flange. I mean, we run into this all the time. Would it be, in your opinion, better to address it from the piping side and just basically anchor the piping down, limit the amount of movement, and make that transition between pipe and flange?
If there was a big concern with the flange, and obviously what you're getting at is you can only make it so thick, or else your hub is getting big and then spot face and you're just taking everything out. If that was truly the issue, I'd look at gusseting the flange. That distributes a whole lot more of the load. It protects the flange face itself, and then it distributes the load to the tank. So I don't know that I'd mess around. Anchors are tough. I mean, they're necessary and flexible piping systems to direct expansion. But to try and just, we kind of want FRP to be somewhat flexible. It's just we have to account for that flexibility. There are ways, it's called the Kellogg equivalent pressure method. I don't know if you guys have ever heard of it, but it's basically taking those reactions that you get from pipe stress and turning them into an equivalent pressure. So if it's 150 psi flange, well, if you add these reactions to it, it might be something like 180 psi flange equivalent design. So that helps you account for a little bit thicker flange without, you know, some people say, give me 150 psi rated flange or 50 psi rated flange. When you actually look at the reactions on that, that could actually double that load on that flange, which is maybe where some of the issues are coming from. But if there was an issue with the flange thickness, I would talk about gusseting it.
Can I say something to this? You know, this is something that, you know, he mentioned the Kellogg approach. This is something that's built into the pipe stress programs now, so a piping designer can consider these things, and you know, he'll see the loads on the flanges because he can evaluate them that way. We talked about yesterday that there's two kinds of nozzle reinforcement repads, and one is like a flat donut that goes around the nozzle. So when we're doing this kind of evaluation, at that point, basically, literally, it's the nozzle connection that you're evaluating. When you have that, like, what do you call the radial force going into is where it's pushing into the tank. You know, the tank has some stiffness, but in the end, you're getting the stress on that, basically that branch connection that ties that nozzle in. If you do the style B, where the repads are running up on the nozzle neck, that's giving you extra reinforcement. We can kind of qualify that to some extent. It's not, you're not necessarily doubling everything, but it's definitely contributing. When we do pipe stress, you definitely have to respect the tank. So, you know, we want to manage thermal expansion so it doesn't create issues at the tank, but you can't just, you know, just kind of isolate that and, like Daryl said, lock it down and try to push everything back into the pipe, because now you create other issues with the, you know, the support drive is, you know, loads into the structure or into the pipe in different places. It's, you know, it's everything is a compromise, and we're trying to look at all the concerns and try to keep everybody happy. The, you know, the fixed asset guy, the structural guy, as well as the piping guy. You know, and that's really the goal. But you know, this is something that, you know, what was interesting once we started going into this, I started talking to a number of engineers in the plants as well as in the engineering companies, and particularly the engineering companies would say, well, you know, the steel tank guys, you know, they kill us with this too. They're like, you know, well, we don't want any loads on our tanks, or, you know, how do we calculate that? How do we qualify that? The steel tank guys, you know, it's a common problem. Even with that, which you think should be all, you know, well known and open, that they don't necessarily know the depth that it takes to look at this either, or they don't want to get into it. You know, everybody wants to kind of manage their liability. So, I don't want any loads on my pump. You know, you see this cast iron housing, you know, it's like a brick that's bolted to the ground, you know, but they don't want to accept any liability, because anything extra put on there, they feel like, well, that might be a problem that, you know, like, I want to hurt and just stay out of that problem. So it's the more that we can communicate between the tank design people and the piping people, the better off we are. And kind of Daryl alluded to, if we can just communicate tank stiffness to the piping people, then they can, you know, start that conversation if I work through that. Do you have a question for me, or is this really his talk?
Working as a former fabricator, it's in what I've seen more as a tank shop. A lot of times the tanks are much longer lead items, and those orders are left before the piping is designed or even there. So I can see how the engineer could come back and provide information of what the nozzle stiffness is, but I don't see it. By the time piping is designed and goes back on the tank side, it's a bit late from my perspective on how my former shop would have been able to handle that information coming back and make any decisions. So I don't know if you have any comments or thoughts. I've seen that several, or I'd likely to have seen that several times.
Like I said, I mean, order of magnitude of stiffness is more important than the physical number that you input. So as long as the issue is known, my long-term goal in this is to have like a non-mandatory appendix in RTP1, where a tank designer, if their nozzles are called out to be, have piping connected to it, they need to consider maybe a little bit extra repad with some sort of calculation or estimation to size their repad appropriately. So maybe it's not as much of an, back and forth at that point. Maybe it's more standardized down the road, but we're nowhere near there yet. So, but the short answer is, I would assume the piping designer should assume, finite stiffness in an order of magnitude that seems reasonable for the design, which you might only need to know the tank diameter, because tank diameter is going to affect it a lot. Larger tanks are going to be much more flexible, smaller tanks are going to be much more stiff. So that's going to be your biggest assumption. Then you can kind of go from there. It's all in the experience of the analyst too. You got to know what you're doing. That's why it's hard for non-FRP guys to do pipe stress analysis, is they don't know all the pitfalls they're getting into. So but that's the way I would do it, because there is a difference. Maybe that's a pipe frame, that's an engineer's pipe frame, is to say that the tank designer and piping manufacturer are going to, be singing Kumbaya together. That's not going to happen, but the issue has to be made known first.
One of the goals that I have is to basically to take some of this information and present it to ASME and possibly get a research project funded to where ASME will approach us and say, okay, well, WRC has done this for steel, we need to do this for FRP now, and get them to fund a research project where we can develop some data to support something to put into RTP1, put into Section 10 maybe, to give designers more data to where they can do those calculations. If you just want stiffnesses, as they're pointing out, really you need to know basically the size of the tank, of the shell, and basically how you're going to build it, what's your line angle. And that's going to put you in a pretty decent ballpark, but you need to have some data to fall back on to really give some concrete direction where we can kind of present something in a structured manner.
Daryl, do you see any differences? Some tanks that we spec out, electrical spec out, grandstand flanges, we see issues like that with nozzle working, basically to get higher stresses on the gaskets to some issues with permeable fluids.
Mm-hmm.
How would that flow match into nozzle works? Now you're not having a full face flat flange to deal with, maybe a little advanced on the lacquer grade. How does that complicate, or does it?
I couldn't hear the first part of your question, Sarah, but it's going to be transferred through the flange some way, right? The one thing I didn't really mention here is there's an important distinction of where you're applying the reactions. Is it at the flange or is it at the tank itself? Because you have a projection of 6 inches, say, of the flange. Well, if you're giving me your vertical force at the flange, well, you're still providing more moment at the connection of the tank shell itself. So you have to be clear if it's at the flange itself or at the tank connection. I know that didn't answer your question, but maybe restate your question so I can hear it the first.
I think what he's saying is that if I have a bandstone flange, like a slip joint flange versus a hard flat face flange,
okay,
does that change the view of how things work or what the concerns
No, I wouldn't
are?
think so. It's all, most of these are irrespective of anything going on in the nozzle or the flange. There is some nozzle stress evaluated, but there's nothing for the flange in WRC. It's everything with the connection and the reinforcement on the shell itself.
I think in the end, the pipe is going to transfer the load to the nozzle, whichever way, whatever kind of flange you have. So the load's going to get there. It's not like it's going to make it slip, because you actually have more sealing pressure on like a bandstone type flange. That's what the goal is. So you're probably going to maintain that contact even better because of that.